Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at implicit differentiation. So I'm just going to start with this example. Y equals x squared. We're going to find the derivative of y to the power of 4. So how would we actually do that? Well, we'd use the chain rule. What we would do is we would move the 4 to the front, decrease the power by 1, and we'd multiply by the derivative of y, which is dy dx. That would allow us to complete the question here. So what we would have is 4y, so y is x squared to the power of 3 times dy dx. Well, dy dx here is just 2x, derivative of x squared. And so we end up getting 8x to the power of 7. That makes sense because if y equals x squared, y to the power of 4 is x to the power of 8. And we know that the derivative of x to the power of 8 is just move the power to the front, decrease by 1, 8x to the power of 7. But I just wanted to show you how the chain rule would work here because we are going to use that in implicit differentiation. So let's look at a question where we would use implicit differentiation. So we're going to use it to calculate the slope of x squared plus y squared equals 1 at this point. So that point is about here, and we're going to calculate the slope of this tangent. Now this is an implicit equation. Neither x nor y is the subject. In fact, this here is not a function. You could rewrite it as two functions combined, like this one here, top one, and also the bottom one, but we're going to use implicit differentiation. So how do we do that? Well, what we're going to do is still follow the rule that we're differentiating term by term. Differentiate this, and then we're going to differentiate that. So the derivative of x squared is just 2x. Now, the derivative of y squared, we're going to use exactly what I showed you on the previous slide. It will be 2y, so move the power to the front, decrease by 1, but then you need to times by dy dx. So we're kind of using the chain rule there. And that equals the derivative of 1, which is just 0. So I want to get dy dx by itself because I wanted the derivative. So in order to do that, I'm going to need to subtract 2x and then divide by 2y. Of course, the 2's cancel out. It's just negative x over y. That tells me the gradient function here. So at the point 0.8, 0.8, gradient of the tangent or the slope is just going to be negative whatever the x value is divided by the y value, which is negative 4 over 3. All right, let's now look at a harder example. So let's use implicit differentiation to differentiate y equals cos inverse of x. This one's tricky. It's not even a function. So what we can do is take the cos of both sides. If we do that, we get cos of y equals x because cos and cos inverse undo each other. So let's implicitly differentiate this. So to differentiate this part, we differentiate cos y, which gives us negative sine y, and by the chain rule, we're going to multiply by dy dx. Now the derivative of x is just 1. So dividing each side by negative sine y, we get dy dx equals negative 1 over sine y. So that's all well and good, but because we had y in terms of x, we want our derivative to be like that as well. So there's a bit of a trick we can use here. So we know the trigonometric identity sine squared y plus cos squared y equals 1. So we can rearrange here to get sine y as the subject. Sine squared y would be 1 minus cos squared y. And now what we can do is square root to get sine y by itself. So sine y will be the square root of 1 minus cos squared y. Okay, so let's substitute this for sine y here. We get negative 1 over the square root of 1 minus cos squared y. And you might be thinking to yourself, how did that exactly help? But see, the thing was that cos y is equal to x. That, of course, means cos squared y is x squared. So here, we have negative 1 over the square root of 1 minus x squared. Now note that this function is only defined for values of x between negative 1 and 1, as is this one. You can't take cos inverse of 2, for example. All right, there we are, we're done. Let's look at a harder example. So this is where implicit differentiation is really useful. Here we have x's and y's in an implicit function, and there's no easy way to get y as a function of x. So how are we going to differentiate? Well, we're just going to differentiate term by term. So the derivative of 10x to the power of 4 is 40x to the power of 3. So now we have to differentiate this. We're actually going to use the product rule. So I'll take the negative 18 out the front. So to use the product rule, we take derivative of the first. So the derivative of x is 1 times by the second plus the first times the derivative of the second. So the derivative of y squared using the chain rule is 2y times dy dx. And we're going to have to differentiate implicitly again here. The derivative of 10y cubed, so we differentiate it as normal basically, and times by dy dx. Now the derivative of 48, derivative of a constant, is just 0. So now we're going to rearrange this equation and get dy dx as the subject. So I've expanded the brackets here. Now to get dy dx by itself, I'm going to factorize just these terms with the dy dx. So to make that happen, get dy dx by itself, I'm going to subtract this here and then divide by that. So there I have dy dx. I'm just going to simplify it because each of the terms can be divided by 2. And then on the bottom I get 15y squared minus 18xy. And then we're done. That is the derivative. It was quite complicated, but implicit differentiation made it easier and allowed me to avoid needing to find y as a function of x first. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.